We've explored how single pulse waves can reflect off fixed end and loose end barriers. Now let's look at standing waveforms. So this is multiple waves in succession. We're going to look at how they reflect off of straight barriers, angled barriers, and rounded barriers, both concave and convex. Let's look at how a standing waveform reflects off a straight barrier. If I send a straight plane wave, it's going to reflect a straight plane wave back. Notice the black wave, this is the black crest compared to the green crest, represent the wave front. So the incident wave front flips around, and now the reflected wave front is at the back. The wave front that leads into the barrier is the wave front that reflects out of the barrier. The speed of the wave coming in, the incident wave speed, equals the reflected wave speed. We know this for a couple reasons. One, the speed's only going to change if it changes mediums. In this case, it didn't change medium. It just reflected. We see that it's covering the same amount of ground in about the same amount of time, and also our frequency isn't changing, and neither is our wavelength. Due to this consistency in the speed of a reflective wave, we can find different variables using the echo formula. So if we send a wave and it bounces off, we know the same speed. We can use that to find the distance and the time. So it's a formula that uses a wave to determine speed, distance, and/or time of a wave. The formula is speed equals 2 times the distance divided by time. When we talk about the speed, it's the speed of the wave. It's how fast it's traveling. The distance is distance between the source of the wave and the barrier. So that'd be this distance here. The front of the wave started and ended at the same distance away from the barrier. Time is the time it takes for the wave to return to the source after reflecting off the barrier. So the wave is sent, it reflects, and it comes back. It has to start and stop at the same place. That's the amount of time. This technology is applied a lot whenever we see sonar. So submarines use it. Naturally, bats and dolphins will use it. This is where we see things like sonar or echolocation. Let's try an example problem. A sound wave is moving with a speed of 1,500 meters per second. Is sent from a submarine to the ocean floor. It reflects off of the ocean floor 5 seconds later. How many meters away is the ocean floor? In this case, we are solving for the distance. It wouldn't be unheard of to have a problem like this that starts with the frequency and wavelength of the wave. So you have to find the speed of the wave before starting the problem. With any problem like this, start with the formula. So speed equals 2 times the distance divided by time. I'm going to substitute in the given information that I know. I know the speed is 1,500 meters per second. I know that it's 5 seconds. I don't know the distance. Now I just need to solve it. I'm going to multiply both sides by 5 to get rid of that division. That'll give me 7,500 on the left, 2 times distance on the right. To get distance by itself, I'm going to divide both sides by 2. So the distance is 3,750 meters. That means that submarine has 3,750 meters before it hits the ground, or the ocean floor. If a wave bounces off an angled barrier, there are a couple concepts to consider. A straight plane wave will reflect an angled plane wave off an angled barrier. So if the wave comes in straight, it's going to come off at an angle relative to that barrier. To understand this angle, we need to look at the barrier, put a perpendicular line, so make a 90-degree angle with the barrier. The first wave, the incidence wave, that's the wave that is moving towards a barrier, comes in at a given angle. It's going to leave at a given angle as well. The angle that it comes in is called the angle of incidence. This is the angle relative to a perpendicular line that an incident wave makes with a barrier. So that measurement right there between the blue perpendicular line and the angle the wave came in at is the angle of incidence. The angle of reflection, this is the angle relative to a perpendicular line that a reflected wave makes with the barrier, is going to be located right there. It's that angle measure between the direction of the reflected wave and the 90-degree perpendicular line that we drew into our barrier. In our observations, you probably noticed that these two angles are very similar. In fact, the angle of incidence is equal to the angle of reflection in all cases when a wave bounces off of an angled barrier. If you send a straight plane incidence wave towards a concave barrier, the wave will converge, the waves converge at a focal point. This is how satellite dishes and eyeglasses work. So if we send a straight wave in, this could be a sound wave, light wave, any type of wave, we send it into a concave barrier, it's going to reflect that wave and converge the waves. Where all three of those waves cross, that's what we call the focal point. Convex barriers act similarly. Concave converges all of the wave. A straight plane, when it's reflected off of a convex, will diverge the reflected wave. So we can look at it this way. Straight wave comes in, and it's reflected at all different angles. What we're actually seeing is the reflected wave will take the shape of the convex barrier, or the rounded barrier. So that wave comes in, and it sends out ripples. This is just like ripples in a pond. So the straight wave comes out as a reflected curved wave.